Now we are going to look at a special case when you have a remainder problem like this. Let's take the example 5 to the power 26, right? Now we have to find the remainder when 5 to the power 26 gets divided by 15. Now you notice that this number, the one which is going to get divided, and the divisor both have something in common. They both have 5 in common, right? So is there a simpler way of doing problems like these? There is. Now before we get into understanding the methodology behind using that simpler method, let me give you another example. Now let's say what happens when we have to find the remainder when 26 is divided by 6. Right, so let's take this as an example. Now when 26 is divided by 6 and we have to find the remainder, now let me just take the long division route. So 6 4 the 24 and I'm left with 2. So I can actually write 26 as the divisor multiplied by the quotient plus the remainder, right? Now what if I divide both sides by 2? Now you notice that 2 is the factor which is common between 26 and 6, right? So what if I divided the left hand side and the right hand side by 2? I get 26 divided by 2, 13 equals, I retain the quotient as it is and I divide the divisor by 2 this time. So this is 3 plus 1, right? So in other words, what I'm trying to say is the same division would probably look like this. If I divided 13 by 3, I'd get a 4 as quotient, so 3 4 the 12 and 1 as remainder, right? So you notice that this computation and this computation are fairly similar, except that this has common factors multiplied all across and this doesn't have them. Clearly this computation is a much simpler computation to perform if these numbers become larger. Now let's come back to this problem. Now in this problem we see that 5 and 5 are common across both of them, right? Just like 2 was common across all of them, 2 was common across the number which is to be divided and the number which must divide so that we get our remainder, right? You notice that the answer to this problem is when this gets multiplied by that common factor, we arrive at the actual remainder that we are looking for, right? So we are going to use this methodology again. So when 5 to the power 26, it must be divided by 15, right? Finding the remainder here is the same as finding the remainder when 5 to the power 26 divided by 5, right? This number is divided by 15 upon 5, right? So I've divided both the number which must be divided and the divisor, both of them by 5, and whatever remainder I get after this operation, if I multiply it back with 5, that should be my answer, right? So let's do this. So now the problem is a little bit simpler. Now the problem is 5, so we need to find the remainder when 5 to the power 25 is divided by 3, right? And then we'll multiply it by 5. So this is what my problem simplifies to. Now let's divide 5 to the power 25 by 3. Now 5 to the power 25, I can write 5 would leave a remainder minus 1 when divided by 3, because 3 into 2 is 6, right? So when 6 divides 5, the remainder is minus 1. So I'll do so this thing leaves a remainder minus 1 to the power 25 when divided by 3, right? So my answer is going to be this thing multiplied by 5. So I get a minus 5, right? But when something is divided by 15 and I get a remainder minus 5, can I have a negative remainder? I can't. So my answer is going to be just simply, I will add a 15 to the minus 5 and get a number between 0 and 15, which is 10. So my answer is 10. So if I were to do this completely, right, if I were to approach this problem So I would have to, find the powers of 5, and I would have to see which one comes close to a multiple of 15, right? However, what I've done is I've removed whatever was common, simplified this problem, and the factor by which I have reduced this and this, the remainder must be multiplied back by the same factor to get the answer. And all the other rules that we studied so far, they apply exactly as they have been applying to all the other situations.